Take a physical, living cultural practice, like weaving, and contrast it with its sterile, academic counterpart in geometry. The distance between the two reveals how we understand knowledge itself. The standard history of mathematics is told as a linear progression of universal logic. It moves from Greece to Europe, stripped of cultural context, presenting a body of formal truths that exist independent of human society. By treating European abstraction as the only pure mathematics, this dominant narrative categorizes all other global knowledge systems as pre-scientific approximations or simply as decorative craft. Ethnomathematics offers a pluralist framework. This viewpoint recognizes that cultural practices, from weaving to navigation, are distinct, rigorous systems of mathematical logic, geometry, and topology in their own right. Acknowledging this shift means we must stop treating mathematics as a static noun. Instead, we have to look at it as an active verb, a specific way of organizing, measuring, and knowing the world. To bridge these cultural practices with academic study, researchers use a process called formalization. This is the act of translating a lived cultural practice into standardized academic mathematical notation. This process successfully reveals deep structural equivalencies. It proves that indigenous design systems and traditional navigation techniques map directly onto academic geometry, algebra, or combinatorics. But this translation creates a central paradox. Researchers are now grappling with the concept of formalization with loss. When a practice is encoded into a pure mathematical model, the embodied ecological and social frameworks that govern that knowledge in the real world are stripped away. Contemporary ethnomathematics integrates the analysis of symmetry groups with the defense of indigenous data sovereignty against computational extraction. Discovering mathematical equivalence is no longer the end goal of the field. It is the beginning of an urgent ethical and epistemological problem. This photograph captures the creation of a South Indian kolam. It's an active, temporal drawing practice anchored in daily household ecology and ritual hospitality. Translated into an academic model, the kolam becomes an Eulerian circuit. The continuous line path drawn around the dot array maps exactly into a planar graph, with distinct nodes and edges. By isolating a subsection of this graph, we identify array grammars, a specific repeating rule determining how the closed loop functions. Here we see an Andean quipu, a completely distinct mathematical system centered on record keeping. Notice the hierarchical arrangement of the primary chord and the variations in the pendant knots. When formalized into a strict data structure, the quipu reveals a highly complex accounting system. The placement and type of the knots prove the use of a decimal positional notation operating through precise summation equations. Expanding this tree graph shows that variables like color and ply direction function as multivalent metadata. These specific binary tags attached to the nodes allow for complex statistical corpus analysis. Finally, look at the precise geometric symmetry and grid alignment in this indigenous beaded bird emblem. It represents a third mathematical system built on rigorous topological constraints. The physical constraints of the beadwork grid function identically to linear algebra transformations. The maker reasons through vectors and symmetry operations to generate the pattern. These formalizations verify that these practices operate as rigorous computational, topological, and algebraic systems. But if we reverse this analytical process and map the sterile academic model back onto the living practice, the epistemological cost becomes clear. Look back at the Eulerian graph of a kolam. What is missing is the null data, the ritual temporality, the physical space of the threshold, and the practitioner's gendered labor. We have to differentiate between formal equivalence, where the math works, and epistemic equivalence, where the actual meaning translates. As these spheres overlap, there is a massive loss of contextual data. This highlights the core danger of pure mathematical legibility. Once cultural knowledge is translated into academic notation, it is entirely stripped of its community context. This detachment explicitly bypasses community governance. Sacred, restricted, or clan-specific knowledge is turned into freely circulating academic currency. When living mathematical practices are made purely legible to academic institutions, they are reduced to vulnerable raw data. This vulnerability created by formalization leads directly into the modern computational frontier, generative AI, and automated pattern classification systems. There is a professional misconception in data science that the open-access digitization of cultural patterns is an objective, culturally neutral good. Scraping digitized archives of textiles, quipu, and beadwork to train large mathematical models treats the resulting images as free inputs, ignoring the physical and material constraints of their creation. This ideology of open access actively violates cultural practices where knowledge is inherently restricted. It ignores protocols governed by season, gender, or clan authority. This computational harvesting operates through the same mechanisms as historical colonial extraction. It transforms communal cultural heritage into private data, effectively turning collective knowledge into institutional capital. Without intervention, the drive to computationalize cultural patterns functions as a massive, automated system of extraction. Addressing this requires a shift in mathematical research ethics. The standard of minimal informed consent must be replaced by deep relational accountability. This is where indigenous data sovereignty frameworks come in, like CARE and OCAP. These frameworks function as hard technical constraints on mathematical modeling. In this architecture, a local context label attached to a mathematical matrix actively blocks unauthorized AI training crawlers. The new standard for data science is that datasets must natively record provenance, restriction, and community authority directly within the code. Researchers must accept a difficult reality for the open source era. Not all knowledge should be digitized, formalized, or made freely available. Mathematics can no longer treat cultural outputs as freely available variables. Community governance must be embedded in the mathematical data architecture itself. This brings us to the methodological concept of refusal, which has emerged as a valid, powerful stance within modern ethnomathematical research. Certain topologies, equations, or algorithms must remain deliberately unpublished by researchers to protect the living practice from extraction. This directly challenges standard academic norms, which view the intentional withholding of data as a threat to empirical rigor and transparency. But true mathematical rigor actually requires ethical accountability. It proves that analytical accuracy and cultural protection are not mutually exclusive. The goal for the field is to build a discipline that respects both formal mathematical elegance and the sovereign right of communities to govern their own knowledge. Mathematical truth resides in a pluralist ecosystem where formal logic remains inseparable from relational responsibility.